Okay, well, so good morning, good afternoon, good evening, depending on when you are viewing this, and welcome to the first of 3 asynchronous lectures for the last 3 lessons of Math 16010. So, just a few quick things. So, all the quizzes at this point in the semester are done, so there's no quiz announcements. I'll have some office hours during my usual class time during the last week of classes, so you guys can take advantage of that if you feel the need to. And so for those of you that have been going to my in-person lectures, if you want to ask me any questions, what you can do is I'll turn on YouTube comments, and if you have any questions, you can say, okay, at this time, 13 minutes and 40 seconds, I have a question, what are you doing here, or why are you doing this step, or why can't I do this instead? Something like that. And with these asynchronous lectures, I'm also going to be going a little bit faster than normal because I can't really ask you guys any questions. So with this, I'll just say, if you need a second to catch up, I'll take my hands away and I'll give you a brief second to pause the video and catch yourself back up. Okay? So other than that, let's go ahead and talk about some numerical integration. So recall from lesson 29 that left and right Riemann sums, the idea behind them is to approximate the definite integral from a to b of f of x dx. And the idea behind this is that we had to use rectangles to approximate these integrals. So that's the idea behind Riemann sums that we've already seen before. So today's lesson is going to be approximating the same integral. So approximates the definite integral from a to b of f of x dx. But in this case, instead of using rectangles, today we're going to be using trapezoids. So using trapezoids. Okay. And so the rule to appropriately accommodate for that is called the trapezoidal rule. Okay. So before we get into that, let's go ahead and recall the following formula of trapezoid areas. So from high school geometry, so if we have this area here, so if we denote this side length here by A, this side by B, and then this side by H, then from lesson 30, what you could do is say, all right, well, I could, break this up into, a rectangle here and a triangle here as before from lesson 30. But since we're going to be dealing with trapezoids quite a bit here, it might help to just have the trapezoid area formula on hand. So here it is. So the area of a trapezoid, okay, that's going to be equal to a plus b over 2 times h. Okay? So that's the formula for the trapezoid given side lengths A, B, and H here. So in this case, we don't need to worry about breaking this up into a rectangle and a triangle. You just have, here's the area of a trapezoid, let's work with that. So this is the area you're going to be needing here. So one way you can think of this quantity here, this A plus B over 2, one way you can think of it is, this is basically the average of A and B. So that's one way you can think of this quantity here, this A plus B over 2. And then you would multiply this by H. Okay? So to see how to apply this formula, let's go ahead and look at example 1. So here we're going to be approximating the same definite integral that we looked at in lesson 29, and we're still going to be using n equals 3 shapes, But in lesson 29, we used rectangles. Here we're going to use trapezoids. Okay? So here, let's go ahead and take a look at what we have here. So our function in this case, f of x, is going to be x squared plus 1. And our bounds are going to be from 0 to 6. So that's going to be our a comma b interval. So one nice thing about this function is that, well, x squared plus 1 is, this case is going to be strictly positive. So because of this, what this tells you is that this definite integral here will give you the area under x squared plus 1 on 0, 6. So that's the importance of this integral right here. So that's your interpretation of this definite integral. Okay? So here's what happens with this. So a couple of things that we've talked about in lesson 29 actually end up carrying to trapezoid approximations here. So what I mean by that is this. So as with Riemann sums, okay, so we're going to have to break up our interval, in this case 0, 6, into n equals 3 subintervals, okay, of equal length, which we will again denote by delta x. Okay. Now, if you recall from either lesson 29 or if you just take a look at the intervals 0 to 6 and say, okay, if I want to break this up into 3 subintervals of equal length, well, what would delta x be? So if you either do that little bit of mental math in your head, or you recall what we talked about in lesson 29, this delta x is going to end up equaling 2. Okay? So the nice thing is that because of this reasoning, the delta x quantity that we established on lesson 29 still holds the same definition as it did there. So in this case, the delta x quantity we talked about in lesson 29 still holds in this lesson. So in this case, it's b minus a, the length of our interval, over n. So in this case, it's going to end up being the number of trapezoids now. So here, delta x is the same as before. Okay? And so is the x of I variable we talked about at that same lesson. So x of I is going to equal a plus I times delta x for I equals 0, 1, 2, and all the way to n. Okay? So in this case, our x sub I is going to be equal to, so x sub I is equal to, let's see, a in this case is 0, because that's our left endpoint, and then plus I times delta x, which is 2. So x sub I in this case is 2 times I, and for I equals, in this case, we go from 0 to n, so in this case n is 3. So in this case, I goes from 0, 1, 2, and 3. So that's the idea behind x sub I in this context that we also talked about in lesson 29. Okay? So to see how we get these trapezoidal approximations, let's go ahead and draw our graph. Okay. So here's x, here's y. So in this case, here's 0. We're going to put 6 right over here. So we'll put 2 right here, and then 4 right here. So our x squared plus 1 graph is going to look something like this. Okay. So now here's how our trapezoidal approximations are going to work. So the thing is that as with less than 29, the base of our trapezoids are still going to lie on each subinterval. So in this case, if we have t sub 1 here, our first trapezoid, so the base is going to end up falling on the x-axis. So here's the base. Okay, so that's not too bad. But now what's going to happen is that these vertices here and here are going to end up depending on the function values at the left and right endpoints respectively here. So in this case, if we have that, this is f of 0, and this is at f of 2, okay? That means that this side length here is going to end up corresponding to this length here, and then this side length here is going to correspond to going from the x-axis all the way to f of 2. Okay, and then so as a result, the last side is going to end up just connecting these two function values. Okay, so that's our first trapezoid. So what you'll notice is that, all right, since the side length here is exactly delta x as per what we've established, what that tells us is that T1, the first trapezoid, has area, which I'll denote by a sub T1, which equals f of 0 plus f of 2 over 2. So in this case, a is f of 0, b is f of 2, and then we divide by 2. And then times h, which in this case will just correspond to 2 here because that will just be delta x. Okay? And so similarly, we go ahead and repeat the same process for, in this case, T2 and T3. So in this case, if we put f of 4 right here, and then f of 6 right here, okay? So in this case, for T2, we already have the length of this leg here for T2, which will correspond to this side here. So in this case, what's going to happen is that for this side length here is going to correspond to the function value on the right endpoint. So in this case, f of 4. Our base is still on the x-axis with length 2. And then the last length will just connect the two function values from f of 2 to f of 4. Okay? So this will be our T2. And then similarly, T3 will have side lengths f of 4 and f of 6. Its base is still on the x-axis of side length 2. And this last side will connect our function values. Okay. Okay. So by similar reasoning as T1, T2 is going to have area a sub T2, which is going to equal, in this case, f of 2 plus f of 4, and then divide by 2, and then times the side length here, which will end up corresponding to 2. Okay. And then similarly, T sub 3 has area a sub T3, which will have side lengths f of 4 and f of 6 here. So f of 4 plus f of 6 over 2, and then times the side length here, which is 2. Okay. So that gives us our total, this will help give us our total area. Now, you might think, okay, well, why can't we just simplify this? Why don't we just, find these areas individually and we go from there? Well, you could, but I'm going to leave these as these expressions for the time being, and you'll see why in a second. So what happens from this is that now the total area of our trapezoidal approximation is just, okay, all we have to do is add these three areas together and then we're done. So a sub total, okay, is going to be the area of the first trapezoid. So in this case, f of 0 plus f of 2 over 2, and then times 2, and then plus f of 2 plus f of 4 over 2 times 2. So this is the area of the second trapezoid, and then add the area of the third trapezoid. So f of 4 plus f of 6 over 2 times 2. Okay. So again, at this point, we can still, go ahead and cancel out these 2's here, but again, we're going to leave these alone, and you'll see why. So what I'm going to do now is I'm going to factor out these 1/2s from each of these terms. So we have 1/2, and then I'm going to factor out these 2's here. So in this case, 1/2 is just what we had from the definition of the area of a trapezoid, so not much there. But this 2 here, as we sort of already talked about, this will end up corresponding to the side lengths of each of these subintervals here. So in this case, that will just correspond to delta x. Okay? So now, what you'll notice is that, and then times, well, let's see. Now we have to add all these function values together. So in this case, we start with f of 0, because that's the only f of 0 we have. But now what you'll notice is that we have 2 f of 2's from each of these terms here we can add together. So we have plus 2 times f of 2, and then plus, we have 2 terms with f of 4 in them, so we can add those together as 2 times f of 4, and then plus just f of 6, because that's the only thing we have left. Okay? So what you'll notice from this is that, okay, so moving this up a bit. So in this case, f of 0 will correspond to our f of x sub 0 value. And then f of 2 will correspond to f of x sub 1. F of 4 will correspond to f of x sub 2. If we focus on this definition of x sub I here, so if we let I equals 0, then we get 0. If we let I equal 1, we get 2. X equal 2, we get 4. And then f of x sub 3 will give us 6. Okay? Now, the reason I wrote it in this way is because of the fact that it's going to help us sort of see where everything gets placed in the general trapezoidal rule that we'll see in a second. So, now that we have that, let's go ahead and start cleaning this up and see what our trapezoidal approximation gives us. So, like I said now, okay, now we can go ahead and cancel these out, this 1/2 times 2. So ultimately, we're just left with f of 0. So in this case, since f of x is equal to x squared plus 1, letting x equal 0 here will just get you 1. Then plus 2 times, well, whatever f of 2 is, so let x equal 2 here to get 5. And then 2 times f of 4, so let x equal 4 here to get 2 times 17. And then let x equal 6 in here to get plus 37. Okay? So, go ahead and add all these terms up, and you should end up with a good old-fashioned 82. Okay? So, this will be our trapezoidal approximation in this case. Okay? So, like I said in the start, I'll give you guys a second to pause the video. Okay? So, now let's move on. So now what we're going to do is we're now going to evaluate the above integral that we just talked about using the fundamental theorem of calculus and then compare the two numbers. So you have the integral from 0 to 6 of x squared plus 1 dx. Okay. So now what we're going to do is, well, now let's go ahead and find the antiderivative of x squared plus 1. So if you apply the antiderivative power rule to each of these two terms, what you should end up with as your antiderivative is x cubed over 3 plus x. Okay. And remember, because you're dealing with a definite integral here, you do not add the arbitrary constant plus c here. You only have to deal with the arbitrary constant if you're dealing with an indefinite integral. Okay? So, from here, if we apply the fundamental theorem of calculus, we go ahead and let x equal 6 in our antiderivative here. So we have 6 cubed over 3 plus 6. And then subtract that with the antiderivative value at the lower bound, in this case 0. So we have 0 cubed over 3 plus 0. So in this case, this is just going to pretty quickly become 0. So then if we just go ahead and clean this term up, you should end up with 78. Okay? So with this, and you compare that with our trapezoidal approximation, which we got as 82, you'll notice, okay, those are pretty close. There's still some error for sure, but they're pretty close. So at this point, you're probably thinking, well, it's good that we have a trapezoidal approximation, but it just seems like we're doing more work to get this. Like, so what's wrong with the Riemann sums? What's wrong with those approximations? Well, let's go ahead and bring those back up, just to see why we focus more on trapezoidal approximations, why those are helpful even though they're a little bit more work. So if we go ahead and draw our graphs of the left and right Riemann sums of the same definite integral that we talked about above, and bringing those pictures from lesson 29 back up, then we had x squared plus 1 was this guy right here. And if you recall, the graph looks something roughly like this. So if our left Riemann sum looks something roughly like this. And if you recall, the left Riemann sum had a value of 46. Okay? And then doing a similar thing with the right Riemann sum gets you that, so this is x and y. So here's our x squared plus 1 graph again. So then in this case, our right Riemann sum graph is going to look something like this. Okay? So in this case, the right Riemann sum that you get is going to end up equaling 118, if you recall from lesson 29. So like I said, even though 82 is there's still some error against the exact value of 78, it's definitely way, way closer to our exact value for our trapezoidal approximation when compared to our Riemann sum estimations. So that basically answers the question of why should I care about trapezoidal approximations? Because trapezoidal rule gives much, 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 much better approximations in general than either Riemann sum does. So, okay. So trapezoidal rule gives much better approximations in general than Riemann sums do. Okay? So now that we have that, let's go ahead and generalize the trapezoidal rule just to see what it looks like in general. So in this case, so like I said before, let delta x equal b minus a over n, and let x sub I equal a plus I times delta x for I equals 0, 1, all the way to n minus 1, and then all the way to n. So then the estimate okay, of the integral from a to b of f of x dx using n trapezoids is, so I'm going to denote the trapezoidal approximation by t sub, in this case t sub n for trapezoid, t for trapezoid, and n for the number of trapezoids we're using. So if we take a look back at our approximation that we got here, you'll notice we have 1/2 because, again, this one because of the divide by 2 here, and then times 2, which will correspond to our delta x. So we have 1/2 times delta x, and then times the quantity. Well, let's see. So what you'll notice is that with the first and last terms here, you notice they only get counted once, but everything else in the middle gets counted twice. So with that reasoning in mind, that should tell you, all right, well, you have f of x, x sub 0, plus, hold on a second. Sorry, my pencil's acting up a bit, my bad. So we have f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus dot 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 plus 2 times f of x sub n minus 1 and then plus f of x sub n. Okay? So like I said, your endpoints only end up getting counted once, but everything else in the middle gets counted twice. So that's the idea behind trapezoidal rule. And a fun little fact that, even though you don't really need this for the homework, it's a nice little fun fact to have. So the trapezoidal approximation for the observant eye, it actually ends up being the average of the left and right Riemann sums. So what I mean by that is you take the left and right Riemann sums, you add them up, and then you divide by 2. Okay? So, like I said, it's not really something that's super important for the homework, this part right here, but it's a nice little fun fact to have just in case you want to think about it. So, if you look back at the left and right Riemann sum formulas back in lesson 29, and you add them up and divide by 2, what you'll notice is that you get this trapezoidal formula exactly here. So that's why I brought this up. And you can also check it by, in this particular case, you can also check these two numbers here and then add them up, divide by 2, and you should end up with 82 here. So, like I said, not super important for the homework, but just a nice little fun fact to have. So, okay. So I'll give you guys a second to pause the video. All right. So now what we're going to do is we're going to now start applying this trapezoidal rule that we just established. So what we're going to do is we're going to apply this to example 2. So use the trapezoidal rule with n equals 4 trapezoids to approximate the integral below to the nearest thousandth. So our integral in this case is going from from 3 to 6 of natural log of x squared plus 4 dx. So if we take a look at our function, so in this case f of x will end up equaling natural log of x squared plus 4. In this case, our interval is 3 to 6. And in this case, as the problem states, well, n equals 4. Okay? So what you should notice from this is that, all right, well, let's go ahead and figure out, well, what are delta x and x sub I going to equal here? So first, so delta x is going to equal, well, the length of our interval, so 6 minus 3, and then divided by n, so in this case 4. So in this case, you just have that delta x is just 3/4, so that's about as much as you can do there. But then x sub I is then equal to, well, you take the left endpoint, 3, and then it's plus I times delta x, which in this case is 3/4. And then this is for, in this case, you go from I equals 0 all the way to, in this case, n equals 4. So 0, 1, 2, 3, and 4. Okay. Now, in this case, what we're going to do is we're going to, as we saw in lesson 29, we're going to create that 2-row chart that we talked about there. So it basically says, all right, so if I equals, whatever value, so in this case, 0, 1, 2, I can count, 2, 3, and 4, then what are our x sub I values going to be? What are the corresponding x sub I values? So in this case, we say, all right, so if I equals 0 here, well, that should pretty quickly get you just 3 plus 0, so just 3. So that's x sub 0. X sub 1, so if we let I equal 1 here, then we just have 3 plus 3 over 4. So in this case, if you just go ahead and add those up, you should end up with 15 over 4 as your fraction, because remember, we will need to deal with fractions here until the very end. Okay, so that's x sub 1. X sub 2 is going to be 3 plus 2 times 3 over 4. So if we go ahead and clean this up, you should end up with 9 halves, because it's 3 times the quantity 2 times 3 fourths, which ends up actually simplifying to 3 halves here for the second term. For I equals 3, we have 3 plus 3 times 3 fourths. So this will actually clean up pretty nicely to 21 over 4. Okay, and then last but not least, if you let I equal 4, then you just have 3 plus 4 times 3 over 4. So these will just cancel out to just 3 plus 3, so we end up with 6. All right. So from here, now let's go ahead and apply our trapezoidal approximation. So we have t sub 4, because n equals 4, is going to equal 1/2 times delta x, which is 3 fourths. So we have 3 fourths times, in this case, so we have f of x sub 0, so 3, so f of 3, and then plus 2 times f of x sub 1, which is 15 fourths, and then plus 2 times f of x sub 2, so 9 halves, and then plus 2 times f of x sub 3, so we have 2 times f of 21 over 4, and then plus, in this case, you only add the last endpoint once, so you only have f of 6 at the very end here. Okay? So, now that we have that, let's go ahead and plug each of these values into our f of x function we have here. So in this case, we have, well, 1/2 times 3 fourths, so 3 over 8. So now we have, okay, so if we let x equal 3 here, we should have natural log of 3 squared plus 4 plus 2 times natural log of, in this case, 15 fourths quantity squared. 15 fourths quantity squared plus 4. And then plus 2 times natural log of 9 halves quantity squared plus 4. Okay. And then plus 2 times natural log of 21 fourths squared plus 4. Okay. And then plus natural log of 6 squared plus 4. Okay. So, clean everything up inside each of these natural logs. You end up with 3/8 times natural log of 3 squared plus 4, that's 13. Plus 2 times natural log of, so if you square 15 fourths and add 4 to that, you end up with a fraction 289 over 16. And then plus 2 times natural log of, well, 9 halves squared plus 4, so that's 97 over 4. And then plus 2 times natural log of this guy, so 21 fourths squared plus 4 is going to end up being 505 over 16. And then plus natural log of 6 squared plus 4, so that'll just get you a nice value of 40. So plug all this beautiful stuff into a calculator, and what happens from this is that if you round this guy to the nearest thousandth, as per the problem statement, you should end up with 9.496. Okay? So that's example 2. So I'll give you guys a second to pause the video and catch yourselves back up. Okay. So example 3. Now we're going to apply the same trapezoidal rule, but here we're actually given a graph of a function in this case. So here what we have is, we have to approximate the area of the shaded region below using the trapezoidal rule with n equals 4 trapezoids. So what you'll notice is that if we let y equal f of x be this curve right here, then what you'll notice is that, well, since it's pretty clear to see that this graph is above the x-axis, then that tells you that your function is positive. So that means the area of the shaded region you're looking for ends up corresponding exactly to the definite integral of f of x dx. So now we got to figure out, well, what are our bounds here. So it's a bit harder to see with this, with the numbers being so small, so I'll go ahead and magnify a few things. So this is negative 20, this is negative 10, this is 0, this is positive 10, and this is positive 20. So because of that, that should pretty quickly tell you that your lower bound is going to be negative 20, and your upper bound will be positive 20. Okay? And I'll also magnify these y values that we'll need as well. So in this case, you'll end up with 40 here. This guy will be 30. This will be 20. This will be 10. And because we'll need this in a second, this part here will be 15. Okay? So now that we have that, we say, all right, well, like we said, our interval is negative 20 to positive 20. So the fact that we have to deal with n equals 4 trapezoids here means you should get that delta x is, in this case, 20 minus negative 20, and then divide by n equals 4. So what you'll notice is that, well, we have a minus negative here, so those negatives will cancel each other out, and you should end up with a good old nice number of 10 here, okay, for delta x. And then that also implies that x sub I, in this case, will be, well, start with the left endpoints. We have negative 20, plus, in this case, I times 10, because delta x is 10. So we have 10 times I as our x sub I value here. And in this case, because we're going from n equals 4, we have I goes from 0, 1, 2, 3, and 4. Okay? So here's what happens from this. So in this case, we have, well, we got I and we got x sub I. So let's draw our 2-row chart that we talked about in the last example. So we have I equals 0, I equals 1, 2, 3, and 4. So in this case, if I equals 0, then we just have, well, in this case, I equals 0 here, so you just end up with negative 20. And then if I equals 1, you have negative 20 plus 10 times 1, so just 10. So 10 goes here. And then if I equals 2, then we have negative 20 plus positive 20, because you have negative 20 plus 10 times 2 now. So this is 0. So then that's x sub 2. Now x sub 3 is going to end up being negative 20 plus 10 times 3. So you end up with 30 here. So that should get you 10. And then similar reasoning will get you x sub 4, which is going to be 20 here. Okay? So as a result of this, well, let's see. That means t sub 4 in this case is going to be, so t sub 4 is 1/2 times delta x, so 10 in this case, and times f of x sub 0, so negative 20, and then plus 2 times f of x sub 1, so negative 10, and plus 2 times f of x sub 2, so 0, plus 2 times f of x sub 3, so 10, and then plus f of 4, or x sub 4, so in this case you get 20. So, like we said, only the endpoints get counted once, everything else in the middle gets counted twice. Okay? So, I'm going to go ahead and get rid of this because we don't need it anymore. So, like we said, so here's what we have. So 1/2 times 10, so that's 5, no problem. So now we're actually going to need the graph here to figure out what are our values here. So in this case, the problem makes it relatively clear where everything goes. So at negative 20, our function value is going to be at, in this case, 20. So because we have negative 20 and positive 20 here. And then plus 2 times f of negative 10. So we have negative 10, comma 30. So 2 times 30. And then plus 2 times f of 0. So go up to here. We have 0, comma 40. So 2 times 40. And then plus 2 times f of 10. So we have 10, comma 20. So 2 times, in this case, f of 10, so 20. And then plus f of 20. So here we have, in this case, 20, comma 15. So that's 15. So then plus 15 goes here. So then at the end of the day, we have 5 times, go ahead and put everything together here. You should end up with 215. So multiply 5 times 215. So you get 1075 is your trapezoidal approximation of this guy right here. Okay. So that's all I really had for the numerical integration lessons. So I will go ahead and see you guys next time when we talk about exponential growth and exponential decay.